So, guys, I have something. I saw something last night that was unbelievable, and it's literally changed the way I think. I watched a Stephen Hawking special on time travel, and it was amazing. So I'm watching this Stephen Hawking thing on time travel, and I'll tell you, what a life that whole wormhole theory is. Like Stephen Hawking's, it's amazing. He's got this wormhole theory. Like we'll eventually be able to get planes and people to go through wormholes to another dimension. And I'm sitting there thinking, this is amazing. Like I want to switch careers. You can be an astronomer or an astrophysicist like Stephen Hawking's. You can work your entire career on one theory. It's never proven, and people say, he's like a modern-day Copernicus. Seriously, in any other career, if you never finished an assignment, you're like, we've given Bob like 40 assignments. He's never finished one, and he's socially awkward. You'd be like, we got to get rid of that guy. He is going nowhere fast. It is amazing. Our smartest people on this planet, I'm watching the Stephen Hawking thing, and I've always kind of been fascinated by that dude. The smartest people on this planet right now throw theories against the wall, bat well below 200, and yet that's where we get all our progress from. That's where we get all our progress from, is all these guys.
So are you brilliant, or are you just socially awkward?
All right, from this morning, one of the shows I watch on ESPN, Colin Cowherd, and it's amazing how much of science, in terms of the advances, the major advances in science, are actually built on thought experiments. And this is true whether we're talking about theories like the famous theory of relativity, general or special theory of relativity, or things in quantum mechanics. And tonight, when we go through this presentation, we're going to be talking about a lot of thought experiments, some of them that were actually conducted in the laboratory, but a lot of them are just perceived. And it's interesting that a lot of science, think of the major advances in science, Copernicus, Einstein, even Newton, began with basically doing thought experiments in their mind, which is essentially daydreaming, thinking through an entire process. And then that led later on to applying the scientific method to perform an actual experiment to prove logically that what they had gone through in their mind was in fact true. So we're getting into quantum theory tonight, and it's a very difficult subject to grasp. Very few people really understand it. And in fact, it's one of those areas where the more you study it, the more it raises questions instead of answers. So that's really kind of the gist of tonight's presentation. It's not so much about knowledge and answers as much as it's about stimulating thought and raising more thought-provoking and deeper questions about our understanding of the universe. So we talked about this last time. The two great pillars of modern science, general relativity, things on a large scale, stars, planets, galaxies, quasars, the curvature of space and time, and then quantum mechanics, things on a smaller level, electrons, photons, subatomic particles. And the way these two realms work are in complete contradiction to each other. They hate each other. And this is the biggest hurdle in modern science today, coming up with one unified theory basically to bridge the gap between these two. Because what happens when things are really, really small is very, very different than how things behave when they're large. We talked about this last time. If I had a baseball in my hand and I was throwing it in the macroscopic world, if I knew how much force I was putting into that baseball and I knew which direction it was going, I could predict where that baseball is going. But if I take that same baseball and I shrink it down 10 trillion times to the size of an electron or a photon of light, a subatomic particle, the rules of the game are totally different. A photon or a subatomic particle can be invisible. It can be in multiple places at the same time. I could throw it through that wall and it would pass through that wall with ease. And it seems from experimental evidence that it can go backwards in time and change the past or change the outcome of a predetermined play. So this is, strange stuff, borderline science fiction, but from observations, at least what we perceive, scientists perceive, we know this to be true. And one of the concepts that we talked about last time was this concept of quantum entanglement. And basically what happens here is you have two subatomic particles, whether they're photons of light or electrons, and through a process unknown to modern science, they can become linked to each other. So what happens is, when you make a measurement of one particle, it automatically changes the state of the partner particle. So if this particle is spinning clockwise, and I make a measurement of this particle, it will automatically cause this particle here to spin counterclockwise through quantum entanglement. Hardly groundbreaking stuff, but when you consider that particle A and particle B could be on opposite sides of the universe and the same effect holds, it seems as though information is traveling instantaneously from one end of the universe to the other across billions of light years. And so that raises the question, can information in the quantum world travel instantaneously from one end of the universe to the other? Or does space itself, as we know it in the macrocosmic world, just simply have no meaning? Space and time have no meaning at the quantum level. A great mystery, quantum entanglement. Spooky action at a distance is what Einstein called it, which is why he was disturbed by quantum mechanics. And quantum entanglement is not just a theory that's being tested in the laboratory. It's actually a practical reality in the world of computing. There's research going on right now to build quantum computers that basically program transistors. Instead of through classical bits, ones and zeros, you use qubits, where you can have multiple states in superposition. In fact, a former colleague of mine that I used to work with when I was in VLSI, very large scale integration, he's doing his master's thesis right now at Mississippi State University on quantum gates, logic gates using quantum bits. And this man right here, Seth Lloyd, is one of the world's leading researchers in the development of the world's first quantum computer. He wrote a book on programming the universe, and he's doing research at MIT right now. You can build very, very powerful computers, even with a handful of qubits. And you could do things like solve very, very difficult problems, such as simulating or breaking all the IP codes on the internet instantaneously, even if you had a computer with a handful of bits, or simulating very, very difficult problems, complex systems like the Big Bang or the expanding universe, the explosion of supernovas. Things that normally take hundreds or maybe even thousands of hours of simulation time could be done instantaneously if you had a quantum computer that had a handful of bits. Now, quantum computers are still in their infancy. They're basically where classical computers were in the 1950s. But in the next 20 to 30 years, if they solve some of these problems, like how to code the classical ones and zeros using qubits, it could revolutionize the world of computing. Quantum entanglement, essential concept for what we're going to cover tonight. Okay, and then we talked about this last time also. One of the most famous experiments in all of physics, Young's double-slit experiment. Conceptually, very easy to understand. Essentially what you have is a plate with two parallel slits in it. You have a light source, and you're shining light through the double slit, and you're observing the pattern that's displayed on the back wall. And it was Thomas Young who originally performed this experiment a couple hundred years ago, did it with sunlight through one slit and then through two slits, and observed basically a fringe pattern or an interference pattern. The inspiration for this experiment was the debate at that time, is light a particle or is it a wave? Isaac Newton, it's a particle. Huygens, it's a wave. So if you have two slits and you're shining light through it, and light is a particle, then like shooting BBs through a double slit, if these photons of light are little particles, you should see two slits or two bands that are displayed on the back wall. And that would be a clump pattern if light is a particle. In other words, each photon is like a little BB that you're shooting through the double slit. That's natural. That's what we expect in the realm that we're in. However, if light behaves like a wave, imagine pushing water waves through a double slit. What happens is each wave goes through the double slit, interferes with itself, and creates an interference pattern on the back wall. And so that is essentially what would be displayed if light was a wave. And the double slit experiment shows that you get an interference pattern when you shine light through a double slit, whether it's a laser or focused sunlight. To set this up, you'll see an interference pattern if light is behaving like waves. Where it gets interesting is when you fire discrete quantums through the double slit, whether it's one electron or one photon. So let's just use electrons as an example. We tend to think of electrons as tiny bits of matter, the smallest piece of matter that you can essentially get to. So if an electron is basically a particle, then when you shoot electrons through the double slit, we would expect to see two parallel bands. However, when they performed this experiment, they saw an interference pattern, and this is what started to raise some questions about the behavior of quantum mechanics. So why do we see an interference pattern instead of a clump pattern when we're shooting electrons through the double slit? So physicists took this a step further and figured, well, if I'm shooting electrons through a double slit, maybe they're interfering with themselves, and that's what's causing the interference pattern. So why not slow this down? Feynman proposed this back in the 1960s. Let's shoot one electron at a time, slow it down so that one electron per second goes through, or whatever unit of time is necessary to ensure that they're not interfering with each other. One electron at a time goes through the double slit. Let's see what pattern emerges when we do this over a period of time. So they performed this experiment, ran it for an hour or so, and over time, they observed a pattern that started to emerge. And oddly enough, it turned out to be an interference pattern. And you can see this happening here from this video. You run this experiment forward for an hour or so, shoot several thousand electrons through, and you see an interference pattern. So 8 electrons, 270, 2,000, up to 160,000 electrons over a period of roughly an hour. And you can see the bright and dark bands here. So now we have an interesting situation or an interesting question. How does this work for individual electrons that we're shooting through the double slit if they're not interfering with themselves? The only logical explanation based on these results is when you shoot an individual electron through the double slit, it clones itself, in other words, makes a copy, goes through both slits at the same time, interferes with itself, and then creates an interference pattern on the back wall. So that's where we get this idea of electrons being in multiple places at the same time. But the reality is, even though the experimental evidence is showing an interference pattern, it's still open to debate among scientists as to what is actually happening. Does the electron clone itself, or how does it quantumly sense both slits as it goes through? Again, one electron at a time. How do you get an interference pattern when you're shooting one electron at a time through a double slit? That's the question of one of the basic questions of quantum mechanics. So you come to this, basically the wave-particle duality of matter. And that is sometimes it behaves like a particle, sometimes it behaves like a wave. So to research this further and to find out what's going on, scientists decided to place a detector at the double slit. So to see which slit the electron goes through as it's forming an interference pattern, they put a detector at the double slit and they decided to peek, essentially, with what's going on. Put a detector at the double slit, fire electrons through, see which slit they go through and how it forms the interference pattern. When they did that, when this happened, oddly enough, the photons and the electrons went back to behaving like particles. In other words, when they put a detector at the double slit, they didn't act like waves anymore and interfere with each other and form an interference pattern. They behaved like particles and formed a clump pattern, as if the photon itself was aware that it was being watched as it went through the double slit. So in quantum mechanics, when which slit or which path information is obtained, electrons and photons, quantums, behave like particles. And you'll see two parallel bands. When which path information is not obtained, and you're not watching, and there's no detector at the double slit, then an interference pattern is formed, as if it was waves. So matter behaves like waves when you're not watching. It behaves like particles when you are watching. Now, the question, of course, is, why is that? One of the most logical explanations is, in order to make an observation in an experiment, you have to somehow interact with the system. So by placing a detector at the double slit, you're interacting with the experiment and you're changing how the experiment behaves. Similar to a baseball. If I want to see where a baseball goes, I've got to shine light on that baseball. Now, a baseball is really, really big. It's a large collection of particles. So even though light has momentum, when I shine it on the baseball, it's not going to change the direction that the baseball goes very much. But if this baseball were an electron, and electrons being the same size as photons, if I'm interacting with the electron, in other words, shining light on it so I see where that electron goes, and they're the same size, I'm going to change the direction that that electron goes. Most logical explanation. Why does the detector cause the interference pattern to collapse? In other words, the wave pattern to collapse. Why does that happen? The most logical explanation is, in order to detect which slit the electrons go through, you have to somehow interact physically with those electrons as they're going through the double slit. So it's similar to shining light on a baseball in order to see where that baseball is going. Baseballs are big. Shining light on a baseball isn't going to change where a baseball goes very much. It's not going to change it at all. If a baseball is an electron, which is the same size as a photon of light, then it could deflect significantly where that electron goes. Fair enough. The problem is, why doesn't the photon of light, if I'm interacting, if that's the most logical explanation, that interacting, the detector is causing the collapse into the two bands or the particle-like structure, if that's the most logical explanation, why does it change the fundamental nature of how matter behaves? In other words, if electrons or quantums are like little particles, like little marbles, and I shine light on them, why don't they just deflect like billiard balls? Why doesn't it just change the direction of where they go? Why does it actually change the nature, the fundamental nature of how matter behaves? In other words, when I'm detecting when I'm detecting the photons going through the double slit, why doesn't it just change the direction that the photons go instead of changing the fundamental nature of how they behave from behaving like particles to behaving like waves? And that's what's illustrated here. Why doesn't light just change the direction of the quantum? Why does it change the fundamental nature of what's being observed? So, bottom line, when I'm observing which slit it goes through, collapses, becomes two parallel bands, behaves like particles. When I don't have a detector there and I'm not watching as the photons go through the double slit, get an interference pattern, it behaves like waves. When I am in quantum mechanics, when I am watching, I see particles. When I'm not watching, it behaves like waves. So the question is, if measuring right here, here's our double slit again. Double slit. Here's our light source where I'm shooting photons. Here's my screen apparatus. If measuring right here is causing collapse from interference pattern to two bands like particles, then can we set up an experiment where I delay my choice to observe which path the photons go through until after they've passed through the double slit? And that's where we get Wheeler's delayed choice experiment. We talked about this last time. So let's just go through this again. You've got 5 regions. 1, 2, 3, 4, 5. Region 1 basically is a gun where you're shooting a photon or other quantum unit toward the double slit. So basically you're shooting a photon of light here. Region 2 That photon is passing through the double slit, unobserved. It either goes through the left slit, it goes through the right slit, or it goes through both slits. Those are the only three possibilities. Region 2. Now, region 3, after it passes the double slit, basically that photon is in transit toward this back wall. This is our detector right here, our screen. So that's region 3. Or I've got a screen set up here where if the photons are coming through the double slit and interfering with themselves, like waves, my screen will capture everything. In other words, it'll capture it as if it was an interference pattern. So that's what region 4 is. Now, here's where it gets interesting. Region 5, behind the screen, I've got 2 telescopes, which are my detectors. The question you asked earlier, what exactly is the detector? In this particular case, it's not something physical at the double slit. For this particular experiment, it's 2 telescopes. Telescope number 1 is focusing on the left slit. Telescope number 2 is focusing on the right slit. Screen is blocking the 2 telescopes right here. However, if I remove this screen, this telescope is going to be focusing on this slit. This telescope is going to be focusing on this slit. That's your detector. So now I can detect which slit or which path that photon goes through. So this is our experimental setup for delayed choice. I got nothing here, so when it passes through, it's not interacting physically with any detector, which could affect the results of the experiment. I've got my detectors right here until after the photon has passed the double slit, wave or particle or whatever form it's in, but before it hits my back wall. So this is my experimental setup. Now, what happens is, once the photon gets into region 3, before it hits the back wall, I have a choice as the experimenter, as the observer, whether I can, so let's go through this. I have a choice of whether to keep the screen in place or to quickly remove the screen just before the photon hits the screen and reveal these 2 telescopes right here, essentially revealing which path information. Let me say that again. Photon is in transit toward the back wall. Just before it hits the screen, as the experimenter, I can quickly remove that screen and reveal this telescope and this telescope right here and essentially detect or observe which path information. When that happens, quantum mechanics tells me the matter should behave like particles. So the question is something physical causing the matter to collapse from behaving like waves to behaving like particles, or is it knowledge? So when I remove this screen, I'm going to see one of 2 things. I'm either going to see a weak flash here. I'm either going to see a strong flash here and no flash here. I'm going to see a strong flash here and no flash here, or I'm going to see a weak flash at both slits. If I see a flash here, that means that the photon went through this slit. If I see a flash here, it went through this slit. If I see a weak flash at both slits, then basically it went through both slits at the same time. So, all right, we'll go through this. Quantum mechanics tells us that interference pattern if the screen is left in place, then I'm not observing which path information. So I should see an interference pattern as if it's behaving like waves. So that's what 4R represents. If I leave the screen in place and the photons hit the screen, then I should see an interference pattern as if it went through both slits at the same time, the electron, interfered with itself like water waves. If I remove the screen and reveal the 2 telescopes, 5R, then I should see a clump pattern as if it went through either one slit or the other slit and basically clumps here or clumps here, like shooting BBs through a double slit. So that's the gist of Wheeler's delayed choice experiment. So we have chosen the method of detection after the photon passes the slits. I'm not detecting here. I'm detecting here after it's passed through. I'm delaying my choice of when to detect when the photons actually hit. I'm delaying my choice to observe how they're behaving until after they pass the double slit. Screen after the fact, wave behavior. Telescope after the fact, particle behavior. So our delayed choice of how to measure the photons determines how the photons behaved at an earlier time in the past. What does that mean? If they pass the double slit, keep the screen in place, get an interference pattern, they're behaving like waves. Remove the screen, I see a clump pattern because I've obtained which path information. We're behaving like particles. The double slit's been around for 200 years. We've been detecting it, and when we do detect it, we see clump. When we don't detect it, we see interference. So Wheeler, 1978, he's thinking, well, what if we set up something like this? What if instead of detecting here, we detect it down here after the electron or photon has passed the double slit? In other words, we detect it at the last minute before it hits the screen. So that's where it starts. We start with a thought experiment. So, after that thought experiment, the real experiment was performed in the laboratory, exactly what you're saying, with the right setup and everything else, in 2007. And this is the source, you can read the paper on it. So it actually was performed. Thought experiment, 78, real experiment, 2007. We're to the point now in science where equipment and technology has advanced to a point where we can perform an experiment like this. Even though you're absolutely right, photons, they travel really, really fast. Exactly all the ins and outs of how it was done, I'll leave that to bedtime reading. So let's just pretend, okay, not pretend, but it actually happened. Experiment was performed. When they pulled the film away, screen was pulled away at the last minute, they observed particle or clump-like behavior. In other words, what was predicted in the thought experiment actually happened in the real experiment when this was done in 2007. Observation created the existence of particles and loaded up a back history, so they went through the double slit as particles, presumably, based on the results of the experiment. And our interpretation, famous last words, our interpretation of the results of the experiment. So obtaining the which path information, regardless of when we obtain it, results in the quantum to behave like particles. So back to this again. This actual experiment was performed, pulled the screen away. I'm delaying my choice of when to acquire which path information. When I delay my choice, I see a clump pattern, experimental data. If I leave the screen in place, I see an interference pattern. So fundamentally, when I don't know where they came from, I see an interference pattern, like waves, like they went through both slits at the same time. When I do obtain which path information, when I do observe which path they went through, I see a clump pattern. And that's essentially the results of this experiment. So, from that, it would appear as though observation alone determined the prior nature of how matter behaved at the quantum level. And we talked about this before. Let's do an analogy here. Let's just kind of conceptualize this. So essentially what's happening is, imagine you have a double slit here, an electron gun back here, and you have your screen over here. So this is kind of like the double slit setup. All right? Again, we're just using an analogy here. This is not real. This is just an analogy. Double slit, screen. I'm firing electrons through my double slit. The results of this experiment here seem to suggest that when I fire them through, if I'm an observer and my eyes are shut while the electrons are going through the double slit, they initially behave like waves. So they leave the gun like they're waves. They pass through the double slit. They're waves, they're waves, they're waves, they're waves. My eyes are shut. They're heading toward the screen, region 3 in Wheeler's delayed choice experiment. I keep my eyes closed. The electrons, again, they're behaving like waves on their way to the screen. Then at the last second, I open my eyes to observe what's happening, and they go from behaving like waves to behaving like particles instantaneously. And it seems as though they were always particles from the time that they were fired from the gun. They left the gun as waves. They passed through the double slit like they were waves. They were heading toward the back wall like they were waves. I'm the observer. I open my eyes at the last second to observe what's happening, and all of a sudden they're behaving like particles. That seems to be what's happening as a result of the delayed choice experiment. And then I got myself into a lot of trouble last time when I talked about this on a cosmic level. We're talking about a distant quasar, because you can now do a thought experiment, Wheeler's thought experiment. Imagine a distant quasar 14 billion light years away that emits a photon of light before the Earth even existed. It travels through space for billions of years. You've got a galaxy or a dense cluster of galaxies surrounded by dark matter, which gravitationally lenses and causes the photon to bend around both paths or one path. So essentially, on a cosmic scale, you've got your double slit. Your light source, your screen, and your double slit. You could either go this way around the galaxy or this way around the galaxy. Billions of years later, present day, you have an astronomer on Earth that decides to observe this quasar, and he chooses a screen type of apparatus. In other words, going back to Wheeler's delayed choice experiment, the astronomer on Earth uses this right here, a screen. So we go forward. As a result of using a screen type of apparatus, the photon behaves as though it went around both sides of the galaxy, and the astronomer would see an interference pattern. However, let's say that astronomer decided instead, just at random, to use a two-telescope pattern and focus on either one side of the galaxy or the other side of the galaxy. If he did that, then instead the astronomer would see a clump pattern. And then the question was raised, and this is an outstanding question, well, what happens if you have two astronomers standing side by side in the same space, and one astronomer uses a screen and another astronomer uses a two-telescope pattern? What are they going to see? That's a great question. And I'm going to attempt to answer that question later on. But before we do, so you guys understand what this is basically saying. So, screen, interference pattern. Two telescope, I see a clump pattern. Again, thought experiment. Has this experiment literally been performed? To the best of my knowledge, no. But it's an example of how you can extrapolate the double slit experiment on a large scale. Screen, two telescope, astronomer, distant quasar, cosmic interferometer, double slit on a large scale, analogous to Wheeler's delayed choice. Either interference if the astronomer has a screen, or clump if the astronomer has a telescope. We'll come back to this. Now, here's what I want to cover. One of the most famous and thought-provoking experiments in all of physics. We just went over Wheeler's experiment. The question is, do the detectors in the double slit experiment physically cause the wave function to collapse, or is it our observations that are causing collapse? So to further answer this question, there was an experiment set up called the delayed choice quantum eraser experiment, which basically asked the question, can we measure a photon's position and then acquire information after it's been measured and determine its nature, wave or particle, after additional information has been acquired? So this experiment was first proposed by Scully and Druhl back in 1982, and the actual experiment was performed in 1999 by Kim et al. And there's actually a great commentary on this by Ross Rhodes at bottomlayer.com. And there's some great videos on YouTube. Now, this is a very complicated apparatus, and I'm going to attempt to explain this as best I can. So let's just go over this. This is a variation on the double-slit experiment. Here's your double-slit, where which path or both path information can be found and erased after the experiment is complete and recorded by the detector. So let's just walk through this. Here's your classic double slit. One slit, another slit. And basically you're firing a photon through the double slit, just like you did before. Photon comes through, only now it's going to hit something called a BBO, a beta barium borite crystal. And what this crystal is going to do is it's going to use a process called SPDC, spontaneous parametric down conversion, to essentially destroy the original photon and create an entangled pair of photons. Two photons which are quantumly entangled, called a signal photon and an idler photon. All right? Photon comes through and creates one photon that goes this way and another photon that goes this way. So that's the beginning of the experiment. Now, from this point, we're going to go ahead and divide just to simplify this and understand this, we're going to divide this apparatus into the northern half and the southern half. So this is the line. Here's the northern half of the experiment. Here's the southern half of the experiment. So let's go ahead and block off the southern half to simplify things. And let's look at the northern half first. Double slit, and basically you're firing, photon comes in, quantumly entangled pair is created. The signal photon goes along the northern path and hits this detector right here. So basically the northern path is very simple. All it is your basic double slit. Double slit here, and then your detector right here. So signal photon goes along the northern path, hits the detector D0. That's all that's happening in the northern path. Very easy. Now, the southern half is where all the action is. So what happens in the south? Let's go ahead and block off the north. And we're actually going to block off this section right here, which is all of this stuff right here. We're just going to look at detector D4 and detector D3. And let's find out what's happening here. Again, photon comes in, quantumly entangled pair is created. Signal photon goes along the northern path. The idler photon goes along the southern path. Now, notice the two lines. Blue line means that it came from the bottom slit. If I follow the blue line here, it goes through this prism right here. It bounces off of this beam splitter. And I'm actually going to go ahead and back up here. These green bars right here are what are called beam splitters. They're 50% beam splitters. What that means is when a photon of light hits this beam splitter, it has a 50% probability of either passing right on through or bouncing off. All right? And you can see that with the lines right here. 50% chance it'll go through, 50% chance it'll bounce off. Same with the red line, which follows the upper slit. Comes through, hits a 50% beam splitter. It's either going to bounce off and hit this detector, or it's going to pass right on through. These silver bars are 100% mirrors, which means when a photon hits this, it bounces off. So let's go back. If a photon comes from this slit right here, it's going to follow the blue path, and let's just say it hits this beam splitter and bounces off instead of going through. It bounces off and hits this detector right here. Likewise, going back, if a photon hits D3, this detector right here, that means it only could have come from this slit right here. Follow the blue line. If a photon hits D3, it could only have come from this slit right here. Likewise, if a photon hits D4, it could only have come from the upper slit right here, red slit. So my idler photon, if there's a hit at either D3 or D4, I have obtained which path information. I know which path it came from. And because I know which path it came from, I should see a clump pattern. Just hold that thought in your mind. All right. Now, D1 and D2, look what happens here. At detector D1, if the photon comes through, it could have passed through this beam splitter, bounced off of this mirror, and then hit another 50% beam splitter, and bounced off it again and hit D1. Or it could have come from the upper slit, passed through this beam splitter, hit this 100% mirror, and then hit D1. Likewise with D2. In other words, if I get a photon hit at either D1 or D2, I do not know which path it came from. It could have come from either the upper slit or the lower slit. And we call this section of the apparatus the quantum eraser section. And really that's kind of a misnomer. It's really more of a quantum obfuscation, because what it's doing is it's making it confusing and impossible to know whether it came from the upper slit or the lower slit. So all you have to know for the southern part of this experiment is if I get a photon hit at D3 or D4, I know which path information. If I get a photon hit at D2 or D1, I do not know the which path information. So, experiment is performed, and you have a coincidence circuit here, which basically looks at coincidence hits of the signal photon hitting D0 and its idler photon hitting one of these other four. If I get a hit at D1, the experimental evidence shows that I get an interference pattern, which is exactly what we would expect. So, photon comes in, I create a quantumly entangled pair, signal photon goes along, hits this detector, idler photon comes, bounces around, ends up at D0 or D1. So the correlation between 0, 1 results in an interference pattern. Hang on, I'll get to this after I'm done. Likewise, when I do the joint detection between 0 and 2, I also get an interference pattern, which is what is expected, because at D2, I don't know which path information. Either be the blue line or the red line. It could have come from the upper slit or the lower slit. Now, experiments performed at 4 and 3. Experimental data, I see a clump pattern, which is also what is expected. So, because I know which path information. So, go ahead and go through this, use a video. Double slit, A and B, barrier with two slits, BBO, in comes the photon. Shoot it through the double slit, it goes through one of the slits, quantum entangled pair is created. Here's my detector D0, it goes through the southern part of the path, and it's either going to hit D3 or D4 initially. If that happens, I know which path information, and then you've got the quantum eraser section, D2 and D1. The quantum eraser section, in other words, if it hits either D2 or D1, I do not know which path information, and I should see an interference pattern. So that's essentially the setup for this experiment. Fire a bunch of photons through, one after the other. Time and location is recorded, and then it hits one of the detectors. Time is recorded. Coincidence circuit looks at the correlation between D0 and one of these other four. Run the experiment for several photons. Going forward, gather the data. Once the data is gathered, you collect it, you analyze it, and then you separate it out. After all the photons are fired, the data is analyzed. I know the x-axis position from D0 and the coincidence, the corresponding coincidence hits for the other 4 detectors. I separate it out. D3 and D4 again, I know which path information. D1 and D2, I do not know which path information. Every single time this experiment is performed, for D1 and D2, I see an interference pattern. Every single time this experiment is performed for D3 or D4, I see a clump pattern. That's the quantum eraser, the delayed choice quantum eraser. So once again, R01 is the correlation between detector D0 and D1, interference. 03, the correlation between 0 and 3. I see a clump pattern. Exactly as predicted by quantum mechanics, because quantum mechanics tells me if I know which path information, then I'm going to see a clump pattern as if the matter is behaving like particles. If I don't know which path information, I'm going to see an interference pattern. Here's where the experiment gets really fascinating. The initial signal photon hit this detector long before the idler photon hit any of these other detectors. It takes another 8 nanoseconds, which doesn't seem like very long, but in the quantum world, it's a lot of time, before the idler photon propagates through this section of the circuit and hits any of these other detectors. However, the signal photon has already hit this detector and made it and registered its information and sent it to the coincidence counter. How does this photon, which is quantumly entangled to its twin, know where that twin is going to end up? That's one of the great mysteries of this experiment. So it's almost as if this photon can look into the future and know where its quantumly entangled pair is going to end up. If it ends up at either D4 or D3, this photon knows ahead of time to display a clump pattern. If it ends up at either 1 or 2, this photon knows ahead of time to display an interference pattern. And you get this result every single time. So it's as if the photon can look forward into time and obtain information in the future about where its quantumly entangled idler photon is going to end up, and then display the results based on that. So what is causing collapse? Original question. Is it physical interaction with the detector? If that were the case, then we should see a clump pattern at D1 and D2. However, we don't see a clump pattern at D1 or D2. We see an interference pattern. The only thing we know, so we don't see a clump pattern at D1 or D2. We see an interference pattern. We always display an interference pattern at D1 and D2. So what else could be causing collapse? The observer's knowledge, which path information, or know which path information. Again, which path, D3, D4, know which path, D1, D2. So based on this experiment right here, the way it's set up, and the results of the experiment, it seems to imply that it isn't physical interaction with the detector, but it's our knowledge, the observer's knowledge of the setup that is causing the collapse from wave-like behavior to particle-like behavior. The only difference, okay, here we go. D3 versus D1. Blue line to D3, I know which path. It came from the lower slit. Red line or blue line to D1. The only difference between D3 and D1 is what the conscious observer, me, knows about the system. That's the only difference between these two. Our knowledge of the system causes different results of how the photon will act. Based on experimental evidence, the only thing I know is my conscious knowledge of how this is set up. And I see interference here, I see clump here. So it's not physical. It seems to suggest that it's not physical interaction with the detector, but the way the experiment is actually set up. So that's the delayed choice quantum eraser experiment. Now, I'll go over one more. I'm just going to go through this quickly. The delayed choice entanglement swapping experiment. This is another version of a delayed choice experiment where we basically have two entangled photon pairs which are fired off, and one goes to a detector, Alice, another one goes to a detector named Bob, and then their quantumly entangled pairs go to a third detector, Victor. So you got a quantumly entangled pair here, a quantumly entangled pair here. One goes here, one goes here. And Alice and Bob make their measurements before. You know what? I'm going to skip over this. We're getting a little low on time. I'll do this some other time. Okay. So let's just say we went over all this and you understood everything I was saying. Delayed choice. I did two experiments here. I did one, the delayed choice quantum eraser, and then the second one. Based on the results of the delayed choice entanglement swapping, as an explanation, it is often said that any attempt to determine which path a particle takes inside an interferometer disturbs the particle and thus prevents the interference pattern from forming. From a modern point of view, however, interference patterns can arise if and only if no information about the path taken exists either on the particle itself or in the environment, regardless of whether or not an observer accesses this information. So, one more time. An interference pattern can arise if and only if no information about the path taken exists, either on the particle itself or in the environment, regardless of whether or not an observer accesses this information. Directly from this paper here, Experimental Delayed Choice Entanglement Swapping. So back to our dilemma here. We had this question last time. We got a quasar that emits a photon of light 14 billion years ago, before the Earth even existed. It travels through space. It hits a dense galaxy. Billions of years later, I've got an astronomer on Earth that chooses to use a screen type of apparatus. Now let's modify this again based on the question that came up. Astronomer number one uses a screen. Astronomer number two is going to use a telescope. These guys are standing right next to each other. They're in the same environment. All right? So, because astronomer number two is using a telescope apparatus, he has obtained which path information. He's in close proximity to astronomer number one, who has the screen. And if they're observing the same photon at the same time, if this assumption doesn't hold, then this is also not true. If they're observing the same photon, then they'll both see a clump pattern because he's obtained which path information. So if you break this down, then he could see interference if he's observing one photon. He could see clump if he's observing a separate photon. This has to be true. That's the claim I'm making based on these two experiments. Am I right? I don't know. Welcome to the world of quantum mechanics.